Okay, good evening. We are now on the 11th presentation. Those of you who have time, you can look at the previous presentations, 10 of them. Now, today, these are all the usual things that you should be asking questions because this is an exercise that is new to India. So, unless otherwise your suggestions and remarks are there, this type of programs will not be successful in India. Now, the brief recap is last time what we talked about is we have talked many things about the choice of the materials. One of them is what we called as the double junction materials, type 2 junction material and Z type of material. Z scheme materials was the possibilities that we were discussing last time. We will be discussing that also this time also. Before that, I would like to simply take up a question that was asked by one of the participants. I will go to the question first. After that, it may be a question for all of you. Therefore, I will tell you those questions first. Read out what is it that the candidate wants. Please describe how we can calculate the rate of hydrogen production. The primary concern is the method of evaluation of photocatalytic performance. Okay, it is some kind of an efficiency of the material. Okay, that is what she is talking about. The primary concern is the method of evaluation of photocatalytic performance, because catalytic performance means from the yield of the product and other things, you will be able to say yield or selectivity or conversion like that. Here, how will you say is the question. If the charge separation efficiency is the parameters to be compared, the rate must not be reported per gram of the catalyst. Okay, I will come to this. We will discuss this. The photocatalytic rate should be compared under conditions where the incident photons are sufficiently absorbed by the reactor with a sufficient amount of photocatalyst. So this is the question that she is asking. So we will be answering this question today. What are the ways that is one of the problems with this type of new research, new area of research. If we have this type of new area of research, first of all, there is no standard technique of reporting the data. For example, here you can report the data as millimoles of hydrogen evolved per unit gram of the catalyst. This is one way. That is what she is referring to as rate. Okay, but that is not enough. We have to per gram of the catalyst and per photon absorption. Okay, how will we take all these things into account? Because catalyst is one, absorption is another, third one is the amount of hydrogen that is evolved, and also how much of hydrogen is evolved per photon absorption. That is the conventional quantum efficiency of the process. So now there is a team working on this. Okay. I hope you are able to see the slides. So now I will show you two pictures. Why am I showing you these two pictures is many of us who are working in this area of photoelectrochemical decomposition of water, we are not aware of how to construct the reactor. Okay, this is a schematic reactor. Okay, using the 3-cell. A is a single cell because there is no separation here, whereas here 2-cell. I hope you are able to see 2 cells, they are separated by a separator. So these are not the only two types of reactors that are possible. Any number of imaginations can be there. You can be giving rise to a reactor of this type. Sometime later we will show you the reactors that we have made. In a schematic manner, we will show you sometime later, not today. Now, what is it that we are trying to do is In the working electrode is the semiconductor electrode. In the working electrode, oxygen will be evolved. In the counter electrode, hydrogen will be evolved. So now we have to measure the hydrogen that is evolving. This can be measured because both of them are gases, therefore by the displacement of water. I hope you have done this experiment in BSc during your bachelor's degree. Anyway, if you are not done, that doesn't matter. It's some kind of an inverted burette wherein you are letting out the gas that is evolved, so that the water will be displacing, the gas will be displacing water. So you can directly measure the amount of the gas that is evolved, but that is not enough. Okay, so therefore that is one of the ways of reporting millimoles of hydrogen evolved per gram of the catalyst, but that is not the correct way of evaluating the catalyst activity in these systems, because we have another variable here simultaneously, that the illumination, how many photons are absorbed. You can put, for example, you will be able to put a photo detector and measure the photon impingement on this semiconductor electrode. But the photon that is impinging on the semiconductor electrode is not all of them are absorbed. So therefore we have to do this. We can do this in many ways. We will take it up in a different manner on a different day. This is called the actinometry. Actinometry means if I were to impinge a photon on it, how many photons are absorbed. So each photon absorbed will give rise to a chemical reaction. So therefore from that we will be able to decide what is the amount of the photons that will be absorbed. So now today we are going to see how these measurements can be reported, or how these measurements can be made quantitative. I hope you remember the question that was asked. So therefore we have to now measure the hydrogen, measure the oxygen. Okay, if we measure both hydrogen and oxygen, and if it is according to the stoichiometry of the water, then only we can say hydrogen are photocatalytically decomposed and oxygen is photocatalytically decomposed. If on the other hand, if any one of them are not stoichiometric, then there is a possibility that hydrogen is evolved from some other source, not from the decomposition of water. In that case, this photon efficiency or the photoelectrochemical efficiency will be different. Now, quickly looking at a few things. One of the most important problems facing humanity in the 21st century is building an enduring, sustainable energy economy. Although fossil fuels can supply the estimated global energy demand well into the foreseeable future, this strategy has catastrophic environmental implications due to carbon dioxide emissions, leading contributor to the greenhouse effect. Why I am telling this here is, all these things are known to you. Nothing is new, but we must know in this context, why are we looking at hydrogen especially, and water decomposition. Both of them, you will see the few of the questions I was asked myself and I answered. The technology of renewable energy also has economic benefits, such as reduced health and environmental restoration costs, job creation, and the intellectual property. By now you would have known intellectual property, because you are going to go into a new area. So therefore it will create a new intellectual property. Many of us, we were jobless, so therefore now photocatalytic decomposition can be our job. Many things can be told like that. Okay, we will not go into all of them. Even though the cost of renewable energy is dropping, it is still major limitation for the implementation of these techniques. For example, maybe one of you may be having this doubt. What is the cost difference between the present fossil fuels and any one of the renewable fuels? The cost difference can be anywhere from 3 to 10 times. Okay, 10 times higher. The renewable, for example, I take hydrogen. If you take fossil fuel, hydrogen will be 5 times. So therefore, that is the problem that is there existing. Continuous technical advances are needed to make renewable energy cost competitive with the fossil fuels and drive the evolution of how we consume energy. Sunlight is an ideal energy source. Even though sunlight is supposed to be free for us, it is not free. I already told you. For this, sunlight is meant for some purposes. From that, we are using it for our benefit, for our fuel. So therefore, it is a cost. Okay, it is an hidden cost. Okay, completely sustainable and delivers more energy to earth in 1 hour than is consumed globally per year. So what is essentially is, if I were to harness 1 hour of the solar radiation completely, it will give me the energy required for 1 full year on earth. Okay, this is only to show you what is the magnitude of the problem that we are facing. Although solar energy holds great promise, its large-scale integration requires efficient conversion of light into storable, usable forms of energy. Among them, water splitting or direct photoelectrochemical conversion of water into its constituent elements and hydrogen and oxygen are the best methods, or one of the best methods. Water splitting, though, will have the farthest reaching impact. The ability to generate hydrogen from water has vast uses in the energy sector, beginning with its storage in a liquid fuel to replace gasoline. There is a need for hydrogen to use in fuel cells, resulting in more efficient and decentralized method of electricity production. Okay, I will tell you only one point here. We have already discussed this, between fossil fuel. If you take the fuel, hydrogen is one of them. If I would take the fuel and electricity, electricity is the most neatest form of energy. Fuel means it will combust. Okay, I have to have a combustion chamber, and then combustion will give you rise to a product that has to be let out in the atmosphere or collected and all those things. Anyway, we will not go into all of them. So therefore, hydrogen is one of them. But if I can produce electricity or electrons, okay, electricity means flow of electrons. So if I can make electrons, that is what is happening in the photovoltaic cells. You take the solar radiation, directly put it on a photovoltaic material and generate electricity. So therefore, if you generate electricity directly from them, it is better, because that is why, for example, you would have already seen solar cells lighting, all those things you would have seen in the signals and other things. But the problem in water is, you will say water is shortage. That is not true. Water is shortage for human consumption, but water is not shortage. Okay, even if water shortage is there, what is required for the whole earth in the form of hydrogen as the fuel is only 0.01% of the annual rainfall that the earth receives. So it is a very tiny amount, or 2 into 10 to the minus 6% of water in the world's oceans. So you can see now what is the magnitude of water that is required to produce the hydrogen fuel for the whole earth. Developing globally viable catalytic materials for this process is the primary focus of this presentation. So now, just to give you an idea, what are the main functions that we have to learn? Definitely we must know some amount of chemistry, some amount of physics, some amount of material science, some amount of environmental issues, and also energy science. In addition to that, we should know some bit of mechanical engineering, chemical engineering, and electrical engineering. Now, here in this picture, what we have shown is, when I take a semiconductor and put a photon, I get an hole and electron. So the electron will undergo reduction, the hole will undergo oxidation. This is all what is possible. But in addition to that, we can have photosensitization, co-catalyst, solid solution, Z scheme, surface interface, surface liquid solution interface, heterojunctions. So we see the whole process requires tremendous amount of interdisciplinarism. In photoelectrochemical water splitting, Heterojunction electrodes consist of two or more dissimilar semiconductors, offer more advantages over those made from single semiconductors. We discussed this last time as the heterojunction or Z scheme. Pairing tungsten oxide with bismuth vanadate, this only one example is given, is a promising strategy that helps to achieve better charge separation and improved overall performance in PEC water splitting. We will show you a picture here where the Z scheme or the heterojunction is working. In this work, they have demonstrated WO3 bismuth oxide titan oxide core. Now we have to think about this again. Core shell model. What is the reason for this? We will have one presentation on that. How the core shell model is beneficial for the PEC of water decomposition or photocatalytic decomposition of water. That we will keep it later on. A detailed valence band edge analysis of the WO3 bismuth vanadate was performed by X-ray photoelectron spectroscopy and ultraviolet photoelectron spectroscopy. It was revealed that due to electronic equilibration between WO3 and bismuth vanadate, Fermi energy level shifting occurs, forming p-n junction at the interface that allows electron from the photoexcited bismuth oxide to be transferred efficiently to tungsten oxide, achieving better charge separation and higher efficiency. This electrode exhibited significantly higher photocurrent, okay, here electricity production density than the individual WO3 and bismuth oxide. I will tell you later on why are we thinking of WO3, okay. The semiconductor is bismuth vanadate, where the photon is absorbed, producing an unprecedented photocurrent of 4.2 milliamperes per square centimeter at 1.23 volts versus a reversible hydrogen electrode under simulated sunlight without the addition of an added catalyst. A thin layer of photocatalytically inactive amorphous TiO2 was deposited onto WO3 bismuth vanadate to react with the surface defects, deactivating them towards surface charge carrier recombination and to increase the stability of the photoanodes. So this is the pictorial representation of that. I hope you have one. Already we have discussed this. So you can see that the photon is absorbed in bismuth vanadate and transferred to the vanadium tungsten oxide. So the energetics of this scheme is shown in figure C. Okay, this is the red line is the Fermi level. This is the tungsten 6 plus and the tungsten 5 plus states. In the same way, valence band WO3 is easily reducible to WO3 minus delta. Okay. So this picture we have already seen. So we have to look at this is only one of them. Okay, you should not think that this is. I will show you a book. A book itself is there on the efficiency calculations of this. I will show you the book in a minute or so. So benchmark efficiency, that is what she is asking, to compare one material to another material to another material. The efficiency of one material for water decomposition to the efficiency of another material. So solar to hydrogen conversion efficiency. This is normally denoted as STH, solar to hydrogen conversion. Okay, this is the benchmark efficiency of any given material for photocatalytic decomposition of water or photoelectrochemical decomposition of water. Whereas diagnostic efficiencies to understand material performance, applied bias photon to current efficiency. So we saw that in bismuth vanadate tungsten oxide, we are applying about 1.23 volts. So therefore, applied bias and photon to current efficiency. Okay. External quantum efficiency is incident photon to current efficiency, IPCE. This is a common terminology. IPCE, incident photon current efficiency, is the common phenomenon, common parameter normally reported in literature for the diagnostic efficiency. Internal quantum efficiency, this is the usual quantum efficiency of any photochemical reaction. photocatalytic decomposition of water or photoelectrochemical decomposition of water is one of the photochemical reactions, because here also you are taking a chemical water, uh, decomposing it to hydrogen and oxygen. So this is the APCE, absorbed photon to current efficiency. Current is called in the, suppose if I were to take 1 mole of photon, that is assume on 1 mole of the photon is absorbed. For 1 mole of the photon, I am generating 1 mole of hydrogen. Okay, I hope you understand. 1 mole of hydrogen is 22,414 ml of hydrogen at NTP conditions. This is another thing that we have to be very careful. If we collect it over water, we have to collect, that is under the vapor pressure of water. So therefore it is not at NTP conditions. So we have to collect it under, we are collecting hydrogen. So let us assume that 10 ml of hydrogen is collected over water. Over water, the water vapor pressure will be there. Therefore, the actual pressure will be different from the atmospheric pressure. So therefore, under those conditions, we are taking 10 ml. Under atmospheric pressure conditions, what is the amount of the hydrogen that we will produce? That is what we have to take as standard state conditions or normal state conditions. So here the whole catalyst system is shown in 3 or 4 regions. I hope you are able to see. In the first region is region represents an ohmic contact. I will come to it in a minute. What is ohmic contact and what is the Schottky contact? Region 2 is a single bond gap N-type semiconductor. Okay, this is an N-type semiconductor. Region 3 is the electrolyte, aqueous electrolyte. Region 4 is the counter electrode. So now I hope you are understanding the science or the electrochemistry is the electrons flow in the external circuit, the ions flow in the internal circuit. So if it is a ohmic contact, then the electron flow will be facile. That is all. So that is why region 1 is called the ohmic contact. A connection between the ohmic contact and the counter electrode completes the circuit. But the ions are transported inside the system, electrons are transported in the outside the system. So now we have already seen all these things, the energy levels that we are plotting inside the semiconductor, and at the interface, the energy levels will be different, and in the presence of the photon, the energy levels will be a dynamic parameter. From that, we are going to a ohmic contact with the counter electrode. This can be a metal, this can be any conducting medium. So now, in the PEC mode, what are the things that we can, how we will be characterizing? Because she asked that question also, what are the characterization techniques that we will use? We will not go into the details of this. This is a list that is UV visible spectroscopy will be used for finding out the band gap of the semiconductor, whether it is a direct band gap or indirect band gap semiconductor. We have already seen all those things. It will be 2 to the power of 2 or 2 to the power of half. We have already discussed all of them. Then open circuit potential gives you the flat band potential. I will come to it, what is flat band potential, but it is an important parameter. Just like Fermi energy, valence band maximum, conduction band minimum, in all those things, flat band potential also is a concept. Then the Schottky barrier or ohmic contact barrier, 3 electrode cyclic voltammetry, light and dark photocurrent onset, IPCE, incident photon conversion efficiency. Okay, 2 electrode, 0 bias potential stack, photocurrent. We have to think about all these things. What is the 2 electrode system? What is 3 electrode system? And what is the advantage and disadvantage? How to make measurements between 2 electrode system and 3 electrode system? How to calculate the efficiencies in out of them? All those things are there. Then we should have a hydrogen and oxygen gas detection system. Can be a gas chromatograph or simply a pressure measuring device. Okay, all these things have to be done. So now you may remember that I have told you that elemental semiconductors are important. Here I have shown you many of these elemental semiconductors in addition to the oxide semiconductors. For example, indium nitride and gallium nitride. These are the two things. You see, indium nitride is so low band gap semiconductor, it can only evolve oxygen, but it cannot evolve hydrogen. Whereas gallium nitride can evolve oxygen, also can evolve hydrogen. So therefore, what it means is, if I were to take if I want to have this, but the band gap is 3.4. If I want a band gap of somewhere here, I can make a solid solution of indium nitride and gallium nitride. That is what is the indium X, gallium 1 minus X, with increasing X from left to right. Okay, with increasing left to right. When I go from gallium nitride to indium nitride, the band gap will decrease. So the band gap will decrease tentatively or intuitively along the red lines that are shown. We will be having an opportunity to talk about the elemental semiconductors if time permits in the coming futures. So the schematic illustration of the main process steps in water splitting: photoexcitation, carrier generation, diffusion, recombination, water oxidation, proton diffusion, and reduction reaction on the surface of the nanowire photocatalyst. Why I am showing this is we have already postulated, I hope you remember, that low dimensional materials will be better for this, not a three-dimensional material, one-dimensional or two-dimensional materials. So here we are showing a one-dimensional material because it is the diffusion can be controlled or can be facile in one-dimensional material. Diffusion of charge carriers, electrons and the holes. Although great progress has been made to date, the fascinating properties of 3, 5. Okay, 3 is gallium nitride. Gallium is 3, nitrogen is 3, 5. On artificial photosynthesis are still yet to be fully explored. Optimum artificial photosynthesis system needs to be simultaneously enhance the light harvesting, charge carrier separation, and transfer and surface redox reactions. It is expected that the effective coupling of excellent photon absorption and charge carrier transfer properties of the 3-5 nanowire arrays with efficient co-catalysts can boost the system efficiency. The development of advanced electrocatalysts with high turnover number. Okay, turnover number, I hope you remember, it is per site. We will have opportunity to talk about turnover numbers later on. Low over potentials for water splitting. I will show you the what do we mean by low over potential and what is the over potential itself in a pictorial way. Okay. Okay. Anyway, in this photoelectrochemical decomposition of water, what is important is the oxygen evolution reaction and hydrogen evolution reaction. Now, even in electrochemistry, the two reactions of great importance is hydrogen evolution reaction and oxygen evolution reaction. Okay, maybe many papers are dealing with the hydrogen evolution reaction. Many papers are also published on oxygen evolution reaction, but the understanding of the oxygen evolution reaction is lower than the understanding. It doesn't mean we are completely understanding both of them. Okay, we are not understanding both of them completely, but understanding of the hydrogen evolution reaction is better compared to oxygen evolution reaction. Okay, I told you about the over potentials. Here I am showing you a pictorially. Okay, we will only take that from this picture, only that, because we are already running late. So now the oxygen evolution potential is here. The dark line is the oxygen evolution potential, but the over potential is this much. Whereas hydrogen evolution potential is the dark line, and the actual potential is this. So you can see the oxygen evolution potential is over potential is higher than the hydrogen evolution potential. And I hope you remember, or once somebody asked a question, I told you always use the value of 0.4 to 0.6 electron volts. 0.4 is normally the oxygen evolution over potential. 0.2 or less than 0.2 is the hydrogen evolution over potential. So I hope you are able to see that pictorially now. So now I'm showing you what is the path that we are taking to achieve that. Okay, what we have to achieve, I have already told you, is at least 33%. Okay, but since it's an electrochemical process, it should be more than the Carnot efficiency. That is why it can be 45 to 50%. So band gap around 3.2, we have 0.1% efficiency. Band gap 2.5, we may be able to get an efficiency of 6%. Band gap 2.1, 15%. Fe2O3. Monoclinic tungsten oxide is the 2.6 electron volts. So now these are the materials that are available now for us. What we are looking at is, if I were to get the efficiency corresponding to 1.23 volts, then that will be without any bias, without any over potential. This graph is drawn by air mass ratio of 1.5. We will come to it later. What is this? So this is the book I was talking to you, Photoelectrochemical Water Splitting Standards, Experimental Methods and Protocols. The slide that I showed is taken from this book only, book and another publications. So now we will come to these pictures a little later. Okay. So we said, since the hydrogen evolution reaction can be enhanced by photocatalyst, platinum metal or something like that, we can also put a co-catalyst here and use the whole ruthenium oxide, for example, RuO2. Then we can use the whole for oxidizing the organic things. So therefore, it is some kind of a pollutant removal. This is a separate subject. We will not deal with it here. So now we have to spend few minutes about we have already talked about tungsten trioxide, molybdenum disulfide. These are all very peculiar substances. Okay, I do not know whether you are aware of all those things. So I will show you a picture. Okay. So now you can see for example, the free energy. Okay, free energy, endothermic, exothermic, all those things are there. So now if you take along the reaction coordinate H plus electron giving rise to half H2, if it were to be in the same line, okay, this is the product energy, this is the reactant energy. Without the barrier, if it is there, then it will be most efficient. So now if I take MOS2 and make the MOS stoichiometric, you see the barrier is high. Okay, because H plus electron, this is all, both of them are zero potential. Whereas if I have 3.3% sulfur vacancy, the barrier is reduced around 1.5 electron volts. Now, if I were to take 15%, then the barrier is reduced completely. If I were to take platinum here as the catalyst for this reaction, platinum, that is why in the electrochemistry, reference electrode is always platinum. So if I were to take, it is very near to the zero energy of the H plus electron or half H2. It will be somewhere here. So therefore, the over potential required is very small. So this is a reason why these systems are important. Here we have shown you direct Z type and heterojunction, which we have shown last time itself. forward backward reactions in Z scheme system with the shuttle redox potential. These are all pictorial representation of all the processes. The only one thing that I have to tell you is, why did I come to the conclusion that the one-dimensional materials are important? This is what is the charge separation mechanism in natural photosynthesis. So in the photosystem 2, we have to spend some time on this, but we have only 4 or 5 minutes now. Anyway, we'll tell this. So now photosystem, the photons is absorbed in the photosystem 2 and then get the excited state. From the excited state, it is the energy transferred to QA, QB, phthalocyanone, iron sulfide, cysteine, like that. So you see, you are having a staircase of the energy levels. Here the potential energy is plotted. Okay, there is no x-axis. X-axis is the distance, but it is not. So therefore, you have various redox potentials that are possible. So therefore, depending upon your substrate, all the redox reactions are taking place. So when the phthalocyanine is formed, then it is comes to the photosystem 1. The photosystem 1 once again absorbs the light and gives rise to A1, A2, A0, F, etc. Then their NADP is getting reduced to NADP. NADP plus is getting reduced to NADP. So you see what we have learned from this. Okay, this is a very complicated system. If we have time, we will have one lecture on photosynthesis itself. Then only you will understand. What is it that is done here is, I will tell you an example. Suppose you are standing in the first floor. I am standing in the ground floor. So we want to shake hands. There only 2 ways are possible. Either you have to come down or I have to go up. So therefore, then only we can shake hands. But you assume that we are now on an escalator. You are in the downcoming escalator. I am in the upcoming escalator. Then we will be able to shake hands in middle way. That is exactly what is happening. So therefore, when I take the electron from the valence band and put it in the conduction band and put it in that conduction band electron into some other system, Z scheme or heterojunctions, the electron energy level is adjusted to the receiving end. So therefore, in a way, Z scheme or multiple component systems are equivalent to the photosynthesis. So now that is why we said that one-dimensional materials or low-dimensional materials will be more efficient. That. So now we are running out of time, so we will not do that. So here the lesson that we have learned is MOS2 or WO3. We will see later on why MOS2 and WO3. You remember this, we will discuss this a little later. The overpotentials, these are all overpotential against the reference hydrogen electrode. So you can see, depending upon the site in the MOS2 itself, when you take the site where the hydrogen is evolved, is the edge site, the overpotential is very low, 0.12 volts. Whereas if I take MOS2 in a graphitic paper, the overpotential is 0.2225 volts. Comparison of potentials needed to reach the turnover frequency of 2 hydrogen atoms per second. Anyway, we will not go into all of them. So this is what we have already seen, and here I got shown how to calculate them. Those of you who want to look at it, you can look at it and ask the questions later on. This is the decomposition potential of not decomposition potential, decomposition heat involved in the decomposition water. P total. So therefore, P total is the so many milliwatts of photons are impinging per square centimeter area of the electrode, I multiply by the electrode, therefore that will give you the proton-photon absorbed. So solar to hydrogen efficiency is millimoles of hydrogen evolved per second into the heat evolved. This is the heat that is divided by the total photon per square centimeter into the square area of the of the electrode. Okay, this is the question that was asked last in the exam. Okay, we have already discussed about perovskites, so we don't have to spend time now. We will take it up as we have already done this. So therefore, the schematic diagram of that. So now, is that scheme perovskite system. This is the core shell model. We will take it up a little later. What is a core shell model and things. So now I will stop at here. And if you have any questions, we can ask questions. Thank you very much. The next presentation will be 3rd May